Assalamu alaikum students. Welcome to today's lecture on heat transfer in the oceans and ocean circulation. In this lecture, we will study how oceans absorb, store and transport heat and why they are so important for the Earth's climate system. We will also discuss the physical processes that transfer heat in the ocean water and the role of ocean circulation in regulating global temperature. In this lecture, our aim is to understand the role of oceans in the Earth energy balance. We will discuss the different mechanism of heat transfer in the ocean water, apply the thermodynamic ideas to ocean systems, and see how temperature and salinity together control ocean circulation. We will also use mathematical expressions to describe how ocean stores and transport thermal energy. The main reference for this lecture is the book by Boyker, which discusses environmental physics from the perspective of energy and climate. In this particular topic, we are particularly interested in how physical laws help us understand the oceans as an important part of the climate system. Oceans are one of the most important components of the Earth system. They covers about 71% of the Earth's surface, so naturally they interact strongly with solar radiation and the atmosphere. Ocean water has a very high heat capacity, which means it can absorb large amount of heat without changing temperature very quickly. Because of this, oceans act as a major thermal reservoir. They store heat, release heat slowly, and redistribute energy from one region to another. And that is why oceans are essential for climate stability. Without oceans, temperature differences between day and night and between summer and winter would be much more extreme. Now we come to the idea of heat capacity. The equation shows here is Q is 𝑚𝑐𝑝 delta T. This tells us how much heat energy is required to change the temperature of a substance. Here this Q is the heat absorbed, M is the mass of water, Cp is the specific heat capacity, and delta T is the temperature change. For water, the value of Cp is quite large, around 4000 joules per kilogram per Kelvin. And this is the key reason oceans can store enormous amount of thermal energy. Even a small rise in ocean temperature corresponds to a very large amount of heat stored. Now we have a numerical example of heat storage in ocean water. We take 1000 kilograms of water and increase its temperature by 2 Kelvin as given by this delta T and this symbol M for the mass. Using the formula Q equals 𝑚𝑐𝑝 delta T, we substitute the values and obtain about 8 into 10 to the power 6 joules. This is more than 8 million joules of heat. So even for a relatively small mass of water, the amount of energy stored is very large. This shows why the oceans are able to buffer climate change and why they warm much more slowly than land. Heat transfer in the oceans mainly occurs through three processes: radiation, conduction and convection. Radiation is the transfer of solar energy into the upper layers of the ocean. Conduction is the transfer of heat through direct molecular interaction, while this convection is the transfer of heat by the movement of the water itself. In practice, all these three processes work together, but their importance is not the same everywhere. For example, at the surface, radiation is important. Within the water, conduction exists but is relatively weak, and large scale redistributions of heat mostly occurs through convection and ocean circulation. Most ocean heating begins at the surface where solar radiation enters the water. A large fraction of sunlight is absorbed within the upper ocean, especially in the mixed layer. This heating makes the surface waters warmer than the deeper waters, creating temperature gradients. Now, these gradients are very important because they drive further heat transfer processes. So, the sun provides the energy, but the ocean decides how that energy is stored and redistributed. Conduction is described by the Fourier's law where Q equals minus K delta T. Here this Q is the heat flux, K is the thermal conductivity, and delta T is the temperature gradient. The negative sign means heat always flows from higher temperature to lower temperature. In simple words, heat moves from warmer water towards colder water. In ocean, conduction does not occur, but compared to large-scale water movement, it is not the dominant mechanism of heat transfer. Still, it is important for understanding small-scale vertical heat exchange. Now here we have a simple conduction example. We take a temperature difference of say 5 Kelvin over a depth interval of 2 meters and use the thermal conductivity of water. By substituting these parameters into the Fourier's law, it gives us the heat flux of about 1.5 watt per meter square, where this negative sign shows us that the direction is from warmer to colder water. Here one can check the things quantitatively, even though the real ocean conduction is often smaller than the mixing and convection. Now, convection happens when warmer, lighter water rises and colder, dense water sinks. This vertical motion transfers heat into ocean. The density of seawater depends mainly on temperature and salinity. Warm water is usually less dense, while cold and salty water is denser. So convection is closely linked to the density differences. Now this process is very important because it allows heat from a surface to be mixed downward and colder water from below to move upward. Now this is one of the most important ideas in physical oceanography. Thermohaline circulation is the large-scale circulation of the ocean driven by differences in temperature and salinity. The word thermo refers to temperature and hyaline refers to salinity. In cold region, especially where seawater is also salty, the water becomes denser and sinks. This sinking motion helps drive deeper ocean circulation across the globe. For this reason, thermohaline circulation is often called the global conveyor belt. It redistributes heat across the earth over a very long time scales. The buoyancy forces determines whether a water parcel rises or sinks. If a parcel is less dense than the surrounding water, it rises. If it is denser, it sinks. This is the same basic physics we use in fluid generally. In the ocean, buoyancy is controlled by both temperature and salinity. So, whenever heating, cooling, evaporation, or freshwater input changes density, the buoyancy forces are affected and circulation can develop. Ocean currents are large-scale movements of seawater. Some are surface currents driven mainly by winds, while others are deep currents driven by density differences. These currents transport heat from warm tropical regions toward colder latitudes. For example, warm currents can make nearby coastal climates milder, while cold currents can cool a surrounding region. In this way, ocean currents play a major role in shaping regional and global climate. Advection means heat transport by the bulk motion of water. Instead of heat simply diffusing molecules by molecule, the water itself moves and carries heat with it. The heat transport equation shown here is Q equals rho Cp V delta T, where this rho is the density, Cp is the specific heat at constant pressure, V is the velocity, and delta T is the temperature difference. Now, this equation shows us that faster currents, large temperature differences, and higher density all increase heat transport, and that is why currents such as Gulf streams are so important for climate. Here we have shown the ocean heat balance equation which describes how energy is distributed at the ocean surface. This equation R of n equals H plus LE plus G means that the net radiation received by the ocean is divided into sensible heat flux, the latent heat flux, and the heat transfer into deeper layers. Sensible heat is the direct heating of air. Latent heat is the energy involved in evaporation, and this capital G represents heat storage or conduction into the ocean interior. Now, this balance is very important because it connects ocean processes with atmospheric processes. Here we have summarized the role of oceans in climate regulations, which shows that why the oceans are central to the climate system. Ocean absorb a very large fraction of excess heat associated with global warming. They redistribute heat through circulation, reduce temperature extremes, and influence weather and rainfall patterns. If ocean circulation changes, the climate patterns can also change. So, the ocean is not just a passive storage system, it is an active regulator of climate. In the summary, oceans act as a major heat reservoir because of the high heat capacity of water. Heat enters the ocean mainly through the solar radiation and is redistributed through conduction, convection, and especially circulation. Temperature and salinity control water density, and density differences drive the thermohaline circulation. Ocean currents transport heat across the planet and therefore strongly influence climate. So, to understand environmental physics and the climate, we must understand the physics of the ocean. Now, the assignment part. For your assignment, I want you to focus on the physical meaning of the equation and the concepts discussed in this lecture. Do not just memorize the formulas, try to understand why oceans can store so much heat, why salinity matters for circulation, and how heat transfer in oceans affect the climate system. And yes, that's all. Thank you very much.